So we are on. We are 2 minutes late, but that's okay because we are here now. That's all that really matters, isn't it?
I was chatting to Rich. We were getting carried away. Sorry about that. We were just nattering about, and it's like, oh, it's 2 minutes past. We better get going. They'll be waiting for us.
Yeah, that's it. Hopefully there will be some people in there waiting for us. I'm sure there will
They're
be.
usually pretty quick to jump on. Yeah, for sure.
Yeah, that's it. That's it. Let me get my screens organized here so I can see anybody that wants a chat. So, where are we? Okay, so we are looking at
Ryan on the beer the bang. 2 minutes late, indeed, sugar.
Oh yeah. That's it. People shouting at us now. I was waiting. Yeah, that's it. Waiting for us. I saw Sugar was in yours last night as well, Rich.
Yeah, we've got lots of biology, chemistry, and sort of math students. I know Ryan was asking some math questions, so you must be doing the triple combo.
Wow. Yeah, Ronnie, just any opportunity to get some maths done, and she is there. Even if it means kind of, I don't know, stealing some of our thunder. She's probably watching this right now, shouting at me.
She'll be logging in and jumping on the chat, trying to hijack it and put some maths in there. No.
Oh, absolutely. But right, who's this? Ryan? I don't even do chem or bio. Really? You've been to most of these, Ryan. What's going on? Just out of interest. Must be. Right. Okay. So last week, some of you wonderful students out there were asking about three main subjects, really. One was about benzene. The other was about rates, and the other one was the Arrhenius equation. That's nobody's favorite thing, okay? So I just thought we'd take a look at these tonight, and I've got a couple of past exam questions that I thought were kind of classics in in two of these areas. Anyway, we won't do any questions on benzene, but with rates and the Arrhenius, just the types of questions you're going to get on this. So, I mean, who's in year two? Who's doing year two chemistry right now? Anybody, done benzene? Anybody done rates or the Arrhenius equation just yet?
I don't even remember the Arrhenius equation, to be honest. I didn't. Was it added to what's now the old spec? I probably did. I wonder if I did the old spec or the old spec. I can't remember. I did mine in 2003, so it would have been.
Yeah, the old spec was 2009 to 2015.
Yeah, so it was the old spec that I did.
Yeah, same as
I don't remember it. I don't even know what exam board I did for chemistry.
It is brand spanking new, the Arrhenius equation, to the new specification. So these lucky people are having to do it, and me, lucky person, has to get his head around it and teach it because I didn't even do it in uni. So yeah, it's all new. But I mean, it looks really scary. But actually, what they want you to do with it is pretty simple. It's like one of three things. Okay, I mean, just rearranging it, using it in a graph, and just plugging some numbers into it. So that's all it is. Okay. So Sugar's on here. Year two chem, not done any of that. Well, that's okay. You're getting ahead of the curve here. Just completed optical isomerism. Well, we talked a little bit about that last week. Great choice of topics. Cheers, Ali. Thank you very much. So where should we start? Well, let's start with some benzene. So I'm just going to fire up the old iPad here, and we'll take a look at what I can do in terms of straightening that can of worms out that is benzene. So let's share iPhone, iPad via cable. There was a bing bong. Is that a Ronnie bing bong?
I don't know. I muted myself, but I don't see. Oh, I'll have to have a look. No, there's still only just the two of us. Ronnie's frantically trying to get the maths course done as much as
yeah. She hasn't had much luck doing many videos of late, so
I know had a bit of a busy time of things. So yeah,
for sure. Right, okay. I'm just trying to sort my screen out here so I can still see the comments and show you my screen at the same time, which is proving more difficult than I want it to be. Right, okay. So like I said, benzene, rates, and Arrhenius equation. So I've had a good intro to these apart from the Arrhenius. Don't worry, that is going to be something that they throw at you at the beginning of the year, but people were asking for it. So I'll just make sure I got a decent pen here. So I'm just after any comments here, folks, about benzene. So what do you know about the structure of benzene so far? What have you actually found out so far, folks? And while you're answering that, I'm just going to draw the general structure of benzene here. If I can.
It's hexagonal.
Oh, better. Yeah, absolutely. Hexagons. Year 2, folks. It's all about hexagons. All about hexagons. So any facts at all about benzene, apart from stuff like it begins with B and ends in E?
I've got one.
Go on in, Rich.
Delocalized electrons.
Boom. Straight in there. That's really, really important. That is why benzene is so special when it comes to its structure. It's absolutely unique when it comes to the structure, things like this. Ali saying that was disproved. Okay, I'm sure I'm going to be waiting with bated breath for finding out what Ali thinks has been disproved. But we've got delocalized electrons. We've got this C6H6 molecular formula here, but it's not an alkene. So there's no C double bond C's in here. Okay. So sugars on here, benzene ring consists of 6 carbon atoms bonded in a flat or planar hexagon ring. Each carbon is bonded to 1 hydrogen because of 3 alternating double bonds. Now, I wouldn't say that they are alternating. This was a structure proposed by a chap called Kekulé. Now, that structure said, like sugar saying, that we've got 3 alternating double bonds here. So 1, 2, and 3. Okay, so essentially what we've got is something like this. So a double bond there, single bond there, double bond there, and a single bond there. And then we've got our hydrogens coming off. Now there's a number of different reasons why this is not the structure of benzene. Number 1, okay, that's because all bond lengths in benzene are the same. Okay, now that's been proven. We can use electron microscopy to actually show that all these bonds are actually the exact same length. We know that double bonds, okay, so these ones here are shorter than single bonds. So we know that all the bond lengths are the same. So that disproves, or one thing that disproves, that alternating single bond, double bond theory, because if that was true, hexagon benzene wouldn't be hexagonal in shape. It would actually look something like this. So you'd have a short bond there, a long bond, a short bond, a long bond, a short bond, a long bond. So that is not a hexagon. So we know that it's not alternating single and double bonds. The second thing, really importantly, no reaction with bromine. Now, what happens with bromine and alkenes, ladies and gentlemen? So what happens if you put aqueous bromine anywhere near an alkene, a C double bond C? Answers on a postcard, or not on a postcard, because that would take ages.
that would definitely take a bit of a while. It breaks them open, doesn't it? It's the test. It's the test for double bonds, from what I remember. Bit of bromine. Absolutely, it is, and it decolorizes. Somehow I just turned into a Blue Peter presenter there, mate. Just like answers on a postcard. I'll send it to my PO box or something. But, so yeah, bromine, okay, will not react with benzene, so it stays orange. Now that again proves that there's no double bonds present, because if there were double bonds present, it would decolorize bromine, and it does not do that. Ali, you're absolutely right. It doesn't undergo addition reactions. It undergoes electrophilic substitution reaction. Yeah, he's on fire, on fire. So third one, okay, it's down to hello, Dexter. Sorry, Dexter loves a bit of benzene. What was I saying? Oh, hydrogenation, okay. So if we look at actually hydrogenating benzene, so we're forcing hydrogen and making it C6H12, it actually takes a lot more energy to do that than we'd expect compared to this Kekulé structure. Now, it would take way too long to go into that tonight, okay, in terms of crunching the numbers, but essentially it's a lot more stable than the alternating single bond, double bond, okay, and that stability is down to these delocalized electrons. It's called a delocalization energy. So that's what makes this molecule really, really stable, okay. Don't be long, Ali. You hurry up there, mate. So that's benzene structure, okay, C6H6, and we've got one hydrogen. We don't usually draw the hydrogens in, okay, it's usually a skeletal form that we draw, and that's what we've got here. But that begs the question, if we've got this structure, I'm just drawing the carbons in here now, and they're not double bonds, okay, they're all single bonds, and there's one hydrogen attached to each of these carbons.
Well, what's that fourth valence electron doing? Because, you know, one electron from this carbon is bonded to that hydrogen, one bonded to this carbon, and one bonded to this carbon. So 3 of its 4 electrons, because don't forget, it's in group 4, are actually used in covalent bonds. Now, these are all sigma bonds, okay, really strong covalent bonds that the carbons form there. Its 4th electron, I'm going to change color here, its 4th electron, so each of those 4th electrons of each of these carbons becomes delocalized. They move around this ring, and that's what that ring is for in the middle of the hexagon. Questions? Benzene dissolves only slightly in water, will float on top of water. Why is that? I'll think about that and get back to you at the end of this, mate. Mass spectroscopy. We did that last week, didn't we, Rich? I'm pretty sure. Yeah, I did that last week. Mass spectroscopy.
Yeah, those absorption peaks. Yeah, so
that's it.
Last week, it'll all be on there as a recording. You can see all the chat and whatnot. It would have been last Tuesday, so go back to 7 days ago and find it on the YouTube history page.
Yeah, it's like 2-3 videos ago. Okay, so there you go. You can find it there. So yeah, these 4th electrons for each of them. So there's 6 electrons. Now these are all pi electrons. Why? Because they are all in p orbitals in the benzene ring. Okay, so you know what? I'm going to go on to the next page here. All right. Oops, no, that's too many pages. Come on, Rich. So again, if I draw out this benzene structure in black, so I'm drawing the hexagon here, nice and big. Okay, now if we look from, if I'm sure you can still see me, you can. If you look from the top of the benzene ring that we're doing here, okay, those p orbitals are figure of 8 shaped, but from above they look like circles, because if you imagine you had 2 just normal party balloons and you put them end to end, that's what a p orbital looks like. It looks like 2 spheres, one on top of the other in this figure of 8 shape. So if you looked at that from above, it would just look like a circle. And that's what I'm going to draw here, because each of those p orbitals from each of those carbon atoms overlaps. So this is the top of the p orbital from that top carbon. This is from that one. This one's from that one, and so on and so forth. Now, if you're looking at that, you can see how all of them are actually interlinked, a lot like the Olympic rings. Okay, so all of these shaded areas that I'm putting in here now, these are all areas where the p orbitals overlap with one another. So if you're an electron in this p orbital, it's easy for you to jump to this one, and then to this one, and then to this one, and then to this one, and so on and so forth. So that's how we end up with those 6 electrons literally just going round and round in circles and being delocalized. Okay, so that is where those delocalized electrons come from. Okay. So that's why they're delocalized, because of the overlap in p orbitals. So you want to put together, I would say you can probably do it in 5 or 6 bullet points. Describe the structure of benzene, and you want to be able to just regurgitate that, because it's so handy. Because at the end of the day, it's these delocalized electrons, this delocalized pi system we call it, or conjugated system, you might read it as well. That is the basis of all of benzene's really special chemistry. Now, I think it was a couple of you already mentioned, these undergo electrophilic substitution reactions. Now, because it's really stable, nothing gets added into the benzene ring because of this delocalized pi system, but it undergoes electrophilic substitution. Electrophilic, why? Because this delocalized system here is really dense in terms of electrons. There's 6 electrons all knocking around in the same area there. So if you're an electrophile, so if you have a positive charge or you're electron deficient in any way, you're going to be very attracted to that area of high negativity, that area of high electron density in the middle of that benzene ring. So nucleophiles such as, anybody name any nucleophiles for me while I just talk about the substitution bit? So put the names of some nucleophiles or the formula of some nucleophiles in there for me. So electrophiles, check. Substitution, why? Because it's really stable. Anything you add into this benzene ring, it's going to take too much energy. It's fine. It's like, you know what? Leave me. I'm perfectly happy as I am. I don't need any extra atoms or anything like that. So, you know what? I'll swap you a hydrogen for something, but I'm not accepting any more in, okay? So Sebastian saying,
so which subshell is more stable, the P subshell or S or D?
in what context, Seb? Which subshell is more stable? I mean, you can't really say one is more stable than the other because each energy level's got, you know, either S, P, and or D electron orbitals in there. So, I mean, the higher the energy, then so the higher the electron kind of shell, then the less stable it is. The most stable ones you'll find most closest to the center of the atom, I think.
1s2, therefore, I suppose. Is it called 1s2?
Yeah, that's it. 1s2, they're the ones right in the middle, they're closest to the nucleus. You know, anything that's not on the outside doesn't get involved in reactions. So yeah, anything that's underneath that then is perfectly stable. So you can't really say one is more stable than the other in terms of types of orbital. So I've got some people stating some, hopefully, electrophiles for me. AJ2, NO3 minus. NO3 minus is not an electrophile.
No, you asked for neutrophils. Was it the neutrophils?
Nucleophile.
Nucleophiles.
You got neutrophils on the brain there, dude.
Yeah, I'm in biology mode. Yeah, so are they, because they are going to be attracted to the positive charge. So I think people are giving us negatively charged groups there: chlorine, OH, NH3, or NH3 is positive.
Yeah. What else we got? NH3. No, that's not either. Okay, so electrophiles are electron deficient. Okay, so we're looking for anything with a positive charge or something that can accept a pair of electrons. Okay, so anything that's negative, bad times. So anything that's positive, actually, we can generate nucleophiles, the NO2 plus. Okay, we can generate a Cl plus. We can even make a Br plus, and there's lots of different ways of doing that. So did I say nucleophile?
You did say nucleophile, and that was
some sort of weird Freudian slip. I must have been, because I think positive. You see, that's the problem. That's what I'm saying. So I meant electrophile. I do apologize, guys. Of course, we're talking about benzene here. So yeah. So positively charged things essentially are going to be attracted to that benzene ring. Now, this is brilliant, right? You've got lots of different things that, yeah, okay, I apologize if I did say that, guys. We've got lots of different things that we need to look at in terms of this electrophilic substitution. So there's a few different electrophiles that we can actually substitute in for a hydrogen on this benzene ring. So there are quite a few of them. So electrophiles are, don't forget, they are electron deficient species. So they're going to be attracted to areas that are highly negative, like our delocalized pi system in this benzene ring. So there's a few different ones here. The ones you need to know are nitration. Okay, so that's a really, really important one where we add, well, we're substituting the NO2 for a hydrogen. We're looking at halogenation. So we're swapping out a chlorine, Cl plus, or a Br plus for a hydrogen. And another one is alkylation, known as the Friedel-Crafts alkylation or acylation. So alkylation is basically where we can add a CH3 plus into that benzene ring, so we can substitute that in as well. So each of these, okay, are unique in terms of how you make those electrophiles. You have to generate those electrophiles first, and we're not going to talk about that here, but we're going to talk about what is the same between them, okay, which is the mechanism for the reaction. It's really, really straightforward, okay. So we always start with our benzene ring. Now, top tip, folks, whenever you're drawing mechanisms, be really, really clear. Take your time, draw nice, big kind of displayed formulae or benzene rings, whatever you're using. So you've got the room to show where those curly arrows are going very, very precisely, okay? So a nice big benzene ring here. What am I going to use? Well, I'm just going to use the NO2 plus electrophile as the example here. Okay, so that could be any of those electrophiles that I've just listed on the left hand side, because the mechanism is exactly the same. So first things first, a curly arrow shows what? Well, a curly arrow in terms of mechanisms shows the movement of a pair of electrons, So where are the electrons? Well, there's none here. Okay, so there's no electrons there. It's actually electron deficient. So there's not going to be a curly arrow from that. All right, let's get rid of that. The electrons, of course, are in the benzene ring. So they're going from that ring to our electrophile. Okay, so that is the first curly arrow that we draw. So this NO2 is attracted to the delocalized electrons, but it's two of those electrons form a bond with that NO2 plus. So we end up with quite an unstable intermediate, actually. So we get our benzene ring like so. And I'm just going to use this carbon here. It can bond to any of these carbons, but essentially we've now got a hydrogen and an NO2 bonded to that carbon. Now you notice how I haven't put that circle in the middle of the benzene ring. Well, that's because we did have 6 electrons forming that complete pi system. That's been broken now. That's been disrupted because 2 of those electrons are now being used to hold that NO2 in place on that carbon, to bond that NO2 in place. So 2 of those electrons are there. So this ring is now broken. So we draw, okay, is it a semicircle? It's a bit more than a semicircle. And we show that that ring is broken. And the whole thing is now positively charged because we've got an imbalance, haven't we? We've just added something that's positive to that benzene ring. So it can't last. That cannot stay like that. This is our intermediate, okay? Now, something's got to give. Something's got to put those 2 electrons back. Remember, it doesn't like being added to. It just likes, you know, things being substituted for hydrogen. So the hydrogen loses out here. The 2 electrons that were bonding in this hydrogen here, they move back into the benzene ring. So the 2 electrons from that bond specifically go back to the benzene ring. And then what have I just said? I said, make sure you give yourself enough room. I'm going to move this over here. And I said that it's substitution. So what we get is our ring back. Okay, now those 2 electrons are back in there. And we've got the NO2 bonded to there. Now this is, of course, nitrobenzene. Okay, that's the name for that. And that's our mechanism for electrophilic substitution. Okay. Question from Ali, why is there just 1 plus in the benzene? If the electrons moved out, would it not be 2 plus? Good thinking there, Ali, but what we've done is the 2 electrons that have moved out of the pi system, they're still part of the molecule, okay? So they are here. If I draw this in red, I'll do a green arrow just so I'm not confusing things. They are there. They're bonding that NO2, so they're still part of the molecule. But because the NO2 came in that was electron deficient with its positive charge, and it's coming into a molecule that had no charge, it just makes the whole thing 1 positive. Hopefully that makes sense to you, mate. So those 2 electrons haven't left the molecule. They're just somewhere else, okay? But they're not in the delocalized system anymore, okay? So as I said, this mechanism here, all right, that will fit for any of those electrophiles that we've got there, okay? So any of these, all right, you can just replace the NO2 with any of those, and that is that mechanism sorted. Always worth a good few marks in an exam drawing a mechanism like this, especially when they can usually ask you, okay, number 1, how you generate, oh, excuse me, go away, someone's trying to ring me, you generate the electrophile, okay, which is different for each of those, so be very, very careful of that. Second is your mechanism. And then thirdly, something after your mechanism, usually they will ask you how your catalyst, because you do need a catalyst to generate those electrophiles in the first place, is regenerated. So it's really 3 steps here that they will usually ask you. But of course, they can pick on any one part of that. So, you know, just be wary, okay? But what I would do is for nitration, halogenation, alkylation, and acylation is very similar as well. So for those 4, make sure you know it from start to finish, how you make those electrophiles and how they're regenerated as well. But your saving grace here is, of course, the fact that your mechanism is exactly the same for all 4 of them, okay? So, that's about it on benzene. It's just a whistle-stop tour, really. Okay, we don't want to get into any more detail on that, but essentially, you know, this is, you know, make sure you understand that structure of benzene, okay? Because like I said, it's the underpinning fact, the underpinning reason for all of its chemistry. All right. And, you know, even when you've got side groups attached, some of you need to know about electron withdrawing groups, electron donating groups, you know, where the bromines attach and why and stuff like that. So, you know, all of this benzene structure is fundamental in answering all of these questions. Okay. So if anybody's hasn't got any questions on that, I'm going to move on and take a look at rates. I think who was here last week? Who was asking me to go through some rates where we look at the data, the experiment data, whereby we use these concentrations, we got this rate, and then we use these concentrations and got this rate. So if you're here, that is exactly what we are going to do now. So has anybody done rates yet?
I'll just jump into this. So Laura says she's got a test tomorrow. I said I put a question on the bottom of the list, which has got a list of things he's working through. It was calculating gaps in orders of reaction tables. Doesn't mean a huge amount to me. Does that mean anything to you?
That is exactly what we're about to do.
Oh, wonderful. There we go.
Yeah.
And there we go. So that's Laura. Your wish has come true. It's not on the bottom of the list. Next on the list.
Absolutely brilliant. So, so hopefully you guys can see this. I take it this is what we are talking about. So with these types of data, what we're looking at are rates of reaction. They did rates of reaction in year one. It's kind of like, oh yeah, you increase concentration and yeah, it increases the rate. Or we decrease the surface area of the solid and it decreases the rate. It was all very qualitative. It was just like, yeah, it goes up or it goes down. Here, we're actually sticking some numbers to it. We're quantifying this now for you, okay? So this isn't a question whereby you've got missing gaps, although there is one here, okay? But it's not quite the same thing. That's more of an Arrhenius thing. But when you're filling in gaps, it's essentially, you know, you're looking at doing the same thing here, okay? So we'll take a look at this question. So we've got hydrogen peroxide, iodide ions, and acid, a classic A-level chemistry reaction here, shown in the equation below. So you've got our acid, sorry, not our acid, our acid there, sorry, iodide and hydrogen peroxide, and it gives us iodine and water. So of course, this is a redox reaction. But if we change the concentrations of each of these reactants, then we're going to change the rate of reaction. And this table shows that. Okay, so determine the rate equation and calculate the rate constant K, including units. Now, the first thing we need to do here is find orders of reaction. And it's just a comparison of the data between the 4 different experiments that we have here. Okay, so we've got experiments 1, 2, 3, and 4. Now it's finding where you have changes in one concentration for one thing, but the others have stayed the same. Remember, probably way back in year 8, your science teacher was talking about making it a fair test, right? Making it a fair experiment where you only change one thing, everything else has to stay the same. And that way we can find out exactly what effect that change there, that independent variable is going to have. And it's no different here, okay? So first of all, we'll look at trying to find the order of reaction for H2O2, so our hydrogen peroxide here. So we need to find 2 of these 4 experiments where it changes, okay? But what we don't want is anything else changing. So we could compare experiments 2 and 3 here, okay? Because it goes from 0.01 to 0.02. But that's no good to us. I mean, this stays the same. That's okay, happy days. But this changes as well. Okay, and that's no good to us. So, you know, we can't tell which of those 2 things is actually changing the rate of reaction here. Okay, so that's no good to us. We can't look at 2 and 3. What we can look at, however, is, if I remember rightly, I'm just trying to figure this out at the same time. So that goes from there, that goes from there. We're looking at 2 and what are we looking at here? I've lost my train. 1 and 2. We can't look at 2 and 3. 1 and 3. 1 and 3. God, I couldn't see the wood for the trees there. 1 and 3. So that doubles. These 2 stay the same, and these stay the same. So the only thing being changed there is our hydrogen peroxide, ladies and gents. Okay. So our hydrogen peroxide doubles. What happens to our rate between examples 1 and 2? Well, that doubles as well. So what does that mean for the order of reaction? Well, the order of reaction for the concentration of H2O2, if we double that concentration, the rate doubles. That means it's first order. Okay, now I should actually, and I will show you very quickly. This is rate, and this is concentration. If you increase the concentration going from left to right and nothing happens to the rate, that's zero order. If you increase concentration, say, and it's a linear relationship, so if you double it and the rate doubles, if you quadruple it and the rate quadruples, that's first order. And second order, oops, that's pretty heavy, but it's exponential. So if you double the concentration, maybe the rate will go up by 2 squared, it'll go up by a factor of 4. So it's absolutely exponential, and that's second order. Okay, folks? So the order with respect to H2O2 is first order. Okay, first order. What's next? We've got I minus. So I'm going to use a different color for this. I'm going to use green. Okay, so we need where I minus is changing, but the other two aren't, and that is this one. Okay, so that doubles there. H2O2 stays the same. H plus stays the same. What's happening here? Well, that doubles as well from 2 to 4. So this is doubling. This is doubling. So in terms of iodide ions, it's also first order. Okay. If you tripled it, the rate would triple. If you doubled it, the rate would double, and so on and so forth. Last but not least, H pluses is getting a bit busy now, but I'm going to do it in red. We can compare these two because that doubles. These two stay the same. Okay, so it's a fair comparison. What happens to the rate here? Well, absolutely nothing. It stays the same. Even though we've doubled the concentration of hydrogen ions, nothing is happening to that rate whatsoever. So in terms of the concentration of hydrogen ions, this is zero order. Okay, so that's how we find our orders with these. Make sure it's a fair test. Make sure there's only one thing that's changing. And then all you have to do is compare that relatively to say, well, you know, how's that affecting the rate? Okay, is it a linear? Is it an exponential reaction? Or is it, you know, have no reaction or no effect on it whatsoever? So once we've got that data, what are we doing with it? Because we need to determine the rate equation and calculate the rate constant. Now, does anybody know, okay, just while I bring my my numbers up here to save me a bit of time, what gets included in the rate equation? Why is it important we find the orders before we write our rate equation, folks? Why is that important?
Ooh, I don't remember any of this, to be perfectly honest with you. I'm just trying to figure out what a sensible answer might be. I'm going to wait and have some help from the YouTube community, I think, on this one.
That's cool.
So I guess so you've got to find the orders first. Is that what you just said? I was replying to your comment. Yeah?
Yeah, absolutely.
It must have some knock-on effect. But what is that knock-on effect?
So our rate expression, if you like, our rate equation is rate equals K, and then you include certain reagents. Some reagents are included, some reagents aren't included. So which ones do you think aren't, mate?
It changes the powers, says Jemima.
She is absolutely right. So what we do is we put in the concentrations of these different reagents to the power of their order of reaction. So rate equals K times the concentration of H2O2. Now that is to the power 1 because it's first order. But you know what? We tend not to actually write that because anything to the power 1 is just itself, right? That's going to be, again, also multiplied by the concentration of I minus to the power 1 because that's, you know, it's first order. All right, so I'm not going to put that 1 there. We don't need to. Now we could actually include H plus as well, but that's to the power 0. Now I was schooled. I was math schooled by Ronnie the other day because a student pointed out to me, and I thought, you know what? I'll check with Ronnie. Anything to the power 0 is 1. Okay, so anything to the power 0 is 1. So essentially, if it's 0 order, it doesn't get included in our rate expression because what's the point of timesing everything by 1 when it'll just stay the same, won't it? So essentially, anything 0 order disappears. Now, of course, this is just this example. If you had something that was second order, it would be squared. That's where it causes a change in the calculation that you do. You have to square that number, okay? But that's our rate expression for this particular experiment, okay? So what do we do once we've got this expression? Oops, didn't mean to rub that out, meant to underline it. All we have to do is pick an experiment. It really doesn't matter which one. You can use 1, 2, 3, or 4. It will give you exactly the same answer. You choose a run or you choose an experiment and you just plug the numbers in. So rate, I'm just going to use the top one here. Let's get rid of that rubbish. Okay, so I'm just going to use the top one here. So our rate in the top one is 2.0. Now be very careful. This is times 10 to the minus 6. Okay, so 2 times 10 to the minus 6 equals k, which is what we want, multiplied by 0.01, which is that value there, multiplied by 0.01, which is that value there. But of course, what we have to do is rearrange. So k equals rate, which is 2.00 times 10 to the minus 6 over 0.01 times 0.01. Now, I've done this previously, okay, just to save a little bit of time. And our answer here is 0.02. And that is our rate constant for this particular reaction. Now, units, this is one thing students always say to me, oh, I'm not really sure, how to do the units on this. Some exam boards, I think it is Edexcel, don't need you to do the units on this, but two of the exam boards do. Excuse me. So our rate expression is this. K equals rate over your concentrations. Now rate, if you look at your units up here, okay, are moles per decimeter cubed per second. Moles per decimeter cubed per second. That's all over. And we've got 2 concentrations down here. So that is moles per decimeter cubed multiplied by moles per decimeter cubed. So once you've got that, okay, once you get that set up, it's just a case of cancelling out. Now this moles per decimeter cubed can cancel with one of these. So I'm just going to choose that one there. Okay, so here you're left with S minus 1 over moles per decimeter cubed. Once you've done your calculations, you can't leave your units like that. You need to bring this to the top here. And when you do that, the powers invert. All right, so what we end up with is moles to the minus 1, because that is essentially moles to the 1. Decimeter cubed, S minus 1. Okay, officially it should start with decimeter cubed per mole per second. Okay, but you know what? They're never going to mark you down for writing it like the way I've just done it. Never.
Can you zoom out a little bit on your iPad, Rich? I think you're writing just off the edge of screen on what's.
Oh, sorry.
I don't know. I'll come back to Zoom. I was looking at just the YouTube video. That's better. It looks like it's centered again now. Yeah, it was just off the air. Oh, it's weird because it's like showing. It's just not centered. If you have a quick look at the, there you go. Yeah, I think it's sorted.
Right. Okay.
It was just for some reason it was just moved off the edge. I was typing comments to Ryan and Ben and Sarah, and I didn't notice. But yeah, no, we're all good.
It's good. Right, we're back. We're back. So yeah, so essentially that's how we do our units as well. Okay, folks. So, I mean, that is everything that it could possibly ask you to do when it comes to these, using these initial concentrations and the initial rates. Okay, so it's about, making sure that when you're comparing 2 experiments, you've got the change in one, but the others stay the same. Make it a fair test. And then, even if the numbers, these are quite nice numbers, these in this actual question that we've got here. Sometimes the numbers you get are awful, all right, but you know what, it's like you can't tell just by looking at them what the relationship is. Is it gone up by a factor of 4? Is it gone up by a factor of 3? So it's just divide one by the other, find the factor. Okay, so divide one by the other, the biggest by the smallest. You can find by what factor it's increased by. So even when you've got dodgy numbers, it doesn't matter. Okay, it really doesn't matter. So that's how we go, and we look at those. Okay, and you know what, 9 times out of 10 you're going to get one of these in the exam. Okay, 9 times out of 10, of course, for the exam that this particular topic is in, you're going to get one of these. Okay, sometimes it might look a little scarier, like maybe this one here. Okay, so like I said, you've got some really iffy numbers here. I mean, that looks really weird, doesn't it? But actually, that just goes up by a factor of 4. Okay, so, you know, use your calculators. Don't be afraid to do that. And yeah, you'll be absolutely fine with those. So do we have any questions on that, Rich? What I was going through, mate? Sorry.
No, I was just talking about some of the competitions that are going to be running next week. We haven't announced any of the competitions, but lots of people saying that they're super keen to win a year's subscription. So there'll be some for biology, some for chemistry, some for maths. So you can win a 4 years biology subscription, 4 years chemistry subscription, or 4 years math subscription. Keep your eyes open. Don't ask me for the details right now because we're not going to tell you. But yeah, keep your eyes open. Be here on, we'll probably announce them Tuesday, I imagine. There'll be lots of stuff all over Instagram as well. If you guys are not following the Instagram account, then that will be part of the competition for next week. So we can you can follow all that then. In terms of chemistry questions, now I think we're pretty much, a lot of people saying that they're not started these topics yet. So I suggest maybe moving on to next topic. What's next on the list? It's also 22, so another 20 minutes or so. If you've got any other chemistry questions.
I mean, somebody asked me about the Arrhenius. I mean, whether these people who were here last week and requested these things are not with us or not. That'd be typical.
If you hear anyone do Arrhenius, let us know. If not, then let's do something else. Let's pick something.
Yeah, absolutely. Anybody particularly want me to talk about Arrhenius, or if you've got any other questions, I can answer those.
Yeah, let's have a look. Yeah, I was mostly just.
Yeah, I'll give you guys just a minute just to kind of, I'll have a sip of coffee out of my cow mug.
So Sarah, was it you who asked to do the Arrhenius? Who's here? Was it I? We're getting lots of yes, do it. So
there we go. Okay, suits me absolutely fine. Okay, so Arrhenius equation. This is it. Okay, this is actually a WJEC question. Okay, yes, Ali, if we've got time, we can have a look at acylation. You mean acylation of benzene rings?
Benzene, yeah.
Okay, yeah, no problem. So this is our Arrhenius equation. Okay, I'm just going to do this in blue. So this is it. Now, essentially, there's only a couple of things that could get you to do with this Arrhenius equation. I'm going to try and go through both. So this is just a rearrangement of the Arrhenius equation. So this is the value of the rate constant K for this reaction at 2 different temperatures is given below. Now, our Arrhenius equation takes into account a few different things. K, of course, is our rate constant. We've just been using that. EA is our activation energy. R is our universal gas constant, so 8.314 joules per Kelvin per mole. That's always given in the question, or at least in your data book, depending on your exam board. T is temperature in Kelvin, okay? And that little e, that's basically just like an exponential, all right? So it's just a button on your calculator for us non-mathematicians, which I am not. I'm not a mathematician. So that is, as far as I'm concerned, just the button in your calculator you need to press, all right? We won't go into it any more than that. But that big capital A, that's a weird one. This is the Arrhenius constant, and it throws a lot of people off. Essentially, we need to account for the fraction of molecules that would react if there was no activation energy, okay? But that's almost never the case. There's like a minuscule chance of that happening. It's just to account for those few molecules. They'll never ask you this, but I'm just qualifying the fact why that A is there, okay? Now that, speaking of which, is what we need to calculate in this question, okay? Yes, it's known as the pre-exponential factor because it comes before that E, before the exponential. So that's just known as the pre-exponential factor, but it's the Arrhenius constant also known as, okay?
Is this year 13 content, Rich, or year 12? I was just
asking. It is very much year 13. Very much year 13, yeah. So unless your teachers have been really mean and started teaching at you when you were doing kinetics in year 1, but I'm pretty sure they wouldn't have done that.
Well, now that it's linear, some teachers I think will start to look at the course and more like we have, and looking at the whole 2-year process and looking at when they're going to introduce the more complicated topics earlier, because very few actually do the AS exams anymore. My personal theory is that the AS exams will basically become obsolete because it costs schools a lot of money to enter students for the exams, and now with the new system the ASs are basically worth nothing. You know, there's not really much value in doing the AS content, so I imagine over time they will disappear and then teachers will have more freedom about how they teach it. That's definitely how we're approaching it at TT this year. But back over to Rich, that's a side topic.
No, yeah, you're absolutely right. You're absolutely right. And I can't help but, you know, when I was teaching in college, They wouldn't need to know something in the first year because we still do ASs in Wales, like AS and A2, they're still separate. But I'd still go into some A2 stuff going, well, you know what, it's interesting. Let's do this anyway, because it kind of makes sense in context sometimes. So yeah, you're absolutely right. So what have we got here? What we're being asked to do, we're given some information. The activation energy for the reaction is this. So this is our EA, and the Arrhenius equation is this. Now, none of the examples ask you to remember this, but you know what? You'll probably see it so many times you'll remember it anyway. So essentially, what have we got? We need to calculate the value of the rate constant K at 295 Kelvin. Now, of course, these are given this rate constant at these particular temperatures, 288 and 300. We've got these rate constants, 0.0761 and 0.2873. Now, 295 Kelvin lies directly in between those two numbers. Not perfectly in between those two numbers, but it's somewhere in between. So logically, and this is the common sense check that you'll hear me talk about in the tutorials and stuff, it's got to be between those two numbers, hasn't it? That really makes sense. 295 Kelvins in between those two temperatures. So our answer, when we get K, has got to be between those two values for our rate constant there, okay? So if you're way, way out, if you get like 500 and something, you know you've done something stupid or you've done something wrong, you've put a dot in the wrong place, or you've forgotten to change some units. You know, it's a common sense check. Okay.
Yeah, and we try and build in as many of these like self-checking processes as possible. I always, with the biology calculations, if it's like a percentage change, like if it's you know, it doesn't have to be that accurate. Maybe it's roughly doubled, in which case you're looking for around about 100% increase. And like if you've done your denominator and numerator the wrong way around, then you end up with like a 50% increase. It's just, you should just be building in the little checking mechanism. Oh, it can't be 50% because it's about double. Therefore, I'm looking for a number in the region of like 80 to 120% increase. It's just all those checking mechanisms really help you to make fewer mistakes on the real exam.
Oh yeah, for sure. And, you know, there's so many examples of that in chemistry as well. You know, I've had students, you know, we're doing pH and it's like calculate the pH of this weak acid. And their answer is like 9.2. It's like, it can't be 9.2. And they're like, why not? I'm like, well, you've known from year 7 that, you know, acids are pH 1 to 7. You know, it can't be 9.2 because that's an alkali. It's not an acid, is it? So, yeah, common sense checks. So what have we got? We need to find, first of all, we've got all these things. We've got EA. We know R because that's always 8.314 joules per Kelvin per mole. All right. So we know EA. We know R. We know a temperature. Okay. Because the one in the question, okay, is actually 295 Kelvin. But the thing is, we don't know A. Nowhere in this question do they give us A. So what we need to do is actually use one of these two figures, okay, using that temperature and that rate constant to find A in the first place. And then when we've got A, our pre-exponential factor, then we can go back and plug in that 295 Kelvin and the activation energy and so on and so forth and see where we're at from there. So it's quite a lot of work here, but it's for 4 marks. So this is the typical thing they'll ask you to do with the Arrhenius equation. And that is, of course, just rearrange it, okay, rearrange it. So I'm going to use this top one here. So I'm using these numbers to find A. So let me just tidy this up a little bit here. Okay, I'm going to get rid of these bits on my scroll and stuff. Okay, so first things first, I'm going to write this equation out again. So what we're saying here is that K equals our pre-exponential factor multiplied by E to the power of EA over RT. I've just put that times in there, so it just gives you a clearer picture. As again, as a non-mathematician, what we need to do in order to rearrange this equation. So if K equals A times that, okay, A must equal K divided by this exponential of minus EA over RT. Okay, so that's what we've got there. And once we've got that, we can just plug the numbers in. And don't forget, I'm just plugging the numbers in from this top one here. You can use either of these. It's absolutely fine. You'll get the same answer. So we have got 0.0761. That's our K for this particular temperature here. That's all over E to the power of minus. Now, what goes on the top? Well, that's our activation energy. Activation energy is 79.333. Or is it? Because in here, there is a tripwire, okay? And that tripwire is units. We cannot use EA and R as they are in their particular format. Why? Because EA, I'm just going to change to red to highlight this, is in kilojoules per mole, all right? Our R, whoops, where did that go? Our R is in joules per Kelvin per mole. You can't put something that's kilojoules and something that's joules in the same equation. It's not going to work out for you. So you need to do one of two things. You either need to turn your activation energy into joules, or you need to turn your gas constant into kilojoules. Either bring one up or bring one down. You need to have them both the same. There's a few examples of this in chemistry. So what I'm going to do is I'm going to multiply this by 1,000 to turn it into joules per mole. Okay, so both of these units end up being the same. So I'm going to get rid of 79.33333, and I'm going to turn that into 79,333. So 79,333, all divided by 8.314. That can stay the same. Multiplied by temperature at 288. Now all of that is e to the power minus that. Okay, so working that out, if you plug that into your calculator, I'm a fan of doing things step by step, then we're going to get 0.0761 divided by minus 33.13, or sorry, e to the minus 33.13. And if we plug that in, we get 1.864 times 10 to the 13. It's just a case of working that out. I've, obviously done this previously, okay, just to save us a bit of time, but you plug that into your calculator, guaranteed that is what you'll get. And that is A. All right, so all of that, and we haven't even answered the question yet. We're only part way there. We found that missing component of the Arrhenius equation, and now we can go ahead and do it for 295 Kelvin, which is what the question was asking. And we can basically just say K equals A multiplied by e to the power of our activation energy over RT. And if we plug those numbers in, so this would be 1.864 times 10 to the 13. Activation energy is the same. R is the same. Temperature is 295. We plug those numbers in and we get 0.167. Okay, and that is our answer, 0.167. And don't forget, common sense check. Okay, does it lie between 0.0761 and 0.2873? Yes, it does. Happy days. Okay, so it's a rearrangement exercise here, folks, a rearrangement exercise. So that is one thing they can get you to do with it. And like I said, this is new to the new specification for everybody. So for OCR, EdXL, AQA, hell, WJEC, okay, Cambridge exam board, I think, is new for as well. It's for everybody. So there aren't actually that many questions of the Arrhenius equation knocking around. So, I'm going to try and come up with some myself in the course, and I'll do my best, but we'll see how we go. But, it is worth looking at all the exam boards questions on the Arrhenius equation and looking at how they all present it, because you know what, there's only so many ways in which they can kind of rearrange this equation or ask you to do something with it. Okay.
Definitely. The same for generally the calculation questions in general, especially with the biology course, lots of those new things, they're going to be, the calculation elements are going to be the same for all the exam boards, whether that's calculating the surface area of a prism, and there's some weird things in there which I don't imagine they're going to ask very often, but it's the same. Calculating, the surface area of a sphere is going to be the same no matter, the exam board doesn't change the rules for the formula for the surface area of the sphere, it's still 4/3 pi r cubed. So use those other exam boards. For those new questions, which are a bit rarer, a little bit less, that come up less often, don't just do the AQA ones, because there's probably loads of OCR questions out there or EdXL questions which are going to be great examples of the same question. It doesn't always ring true for the entire paper, but those calculate questions especially are going to be super handy to just dip in with someone else, another exam board, and see how you go.
Oh, for sure. Absolutely. I mean, there are differences between exam boards and everyone really worries about that. But, for biology and chemistry, the fundamental stuff it's right throughout all the exam boards, isn't it? Yeah. So even like WJEC and Cambridge papers, you know, if you can find them, brilliant. And you know what? Our ultimate subscribers, they get access to that past paper library that we've got. There are, you know, enough past papers there to see you through your A levels and
I'd say
university and
literally
beyond.
I couldn't be 100% sure there's more than 999, but I know I have in the biology section, there's all the old spec for AQA, OCI, EdXL. So that's what, 2009 to 2015. That's 6 years worth with 4 modules per year for 3 or 4 exam boards. There's hundreds and hundreds of biology papers. I imagine for chemistry and maths is just the same. So I bet we're over 1,000 past papers in the past paper library.
I've got pre-2009 stuff in there as well. So I've got the specification papers that we did, mate.
Yeah, I can find mine. Yeah, GLI A-level biology, EdXL 2003. I'll have a look at my old paper. Yeah, I've got some. I don't know whether all of my pre-2009 papers are in there. I have a lot, especially not the OCR, AQA and EdXL. I think I've got them, but I don't know if they're complete. And if you've got an awesome Dropbox folder somewhere out there, you're watching this and you think it would be, you just want to share exam papers with people, send them through to us. Those folders of our past paper library are not actually owned by us, but we know the people who own them, so we can get files added to that. If there's things missing from there, just let us know and we can get some stuff added to it.
Oh yeah, for sure. So yeah, the more the merrier, essentially. So I'll show you the other major thing that they do with the Arrhenius equation here, and that is this graph here. Okay, so ln k against 1 over t. Now this is a rearrangement of the Arrhenius equation. Okay, and where this graph comes from, I'll go through. You know, I'll just go through very, very quickly with you. All right, before we look at this question. Sorry, bud.
Can you zoom in just a little nudge?
Yeah.
Yeah. Can you just make it just a text? I mean, I'm not watching full screen in YouTube, so I'm sure most people are going to be similar to that. It's just a tiny bit hard to read.
Right. We got there.
Also, we're about 1 o'clock, so we'll probably start beginning to things round off. If you do have any other questions, then drop them in.
Yeah, that's it. So I'll go through this real quick. So this is just filling in the gaps in the table, you know, 1 over t. I'm pretty sure you can just do 1 divided by 290. Ln k, okay, so that's the natural log of k. So all you need to do is use that button on your calculator and you'll get this value here. So literally, they're just asking you to plot that graph, okay? And the gradient here, okay, that equals minus EA over R. All right, so that's it. So if they're asking you to find the activation energy of the reaction, all you have to do is just rearrange this. You find the gradient, literally rise over run. Okay, that's the way I've always remembered it. I think I was taught that back in like year 8 or something like that. And essentially, activation energy equals gradient times R. So you find the gradient, you multiply it by 8.314, and you find the activation energy of the reaction in joules. Okay, so I won't go into where this graph comes from and stuff like that. You know what, you'll have to wait for the tutorial on that. But yeah, the graph is the other thing. Okay, so the graph is the other thing. It's basically a y equals mx plus c graph. If you take the natural log of the entire Arrhenius equation, you end up with something like that, and it's just a line. Now I know this is minus EA, but because your gradient is negative, okay, because it's going down, then they cancel each other out, and you basically just end up with the activation energy. Okay, so activation energy equals the gradient in a line times R. And if you can actually find where that line, if I zoom in a little bit more, if this line kind of crossed the y-axis on the scale, where it crosses the y-axis, another really important thing here, that's the natural log of your pre-exponential factor. That's ln A. So it's 2 really important things that this graph can actually show you. It can allow you to find the activation energy of a reaction, and it can allow you to find the pre-exponential factor as well. So 2 things you can get from this graph. And if you want to know exactly, where all these things come from, this is the abridged version. You need to look at the tutorial, which I recorded. It's just in for editing.
Yeah, no, that's all good. I'm just going to say the 2 quick questions that we'd like to the students would like you to just answer as quickly as we can is, from Wada, can you explain the reaction profiles for SN1 and SN2 mechanisms? I don't have a clue what that says, but they're the words anyway. And Ali set the question before, can you just quickly run over the mechanism for acylation in benzene?
Absolutely. So SN1, SN2, guaranteed you are an EdXL person because it's only EdXL that need to know SN1 and SN2 mechanisms. You know what? I think that'll have to be something that we put down for next week. All right. Yeah. I'm sure there's, well, yes and no. I quite how many EdXL people are watching and going to be watching next week. I don't know. So water, then yeah, no, that'll be next week. Okay, we'll talk about that next week. I promise. I'll make a note of that.
So let's tie things off with the mechanism for acylation in benzene. Just
absolutely. So if we go back. Okay, so essentially, as I mentioned before, if we just zoom in on this, nice and big, that is your mechanism for acylation, okay? So for acylation, what we end up with, what we're looking at, let me just get rid of this. Okay, we're not using NO2. We're adding an acyl group, okay? Now your acyl group, I'll do this in blue. Your acyl group comes from an acyl chloride. So something like this, really, really reactive. It's a carboxylic acid derivative as an acyl chloride. What we use is AlCl3 as our catalyst, okay? It acts as a halogen acceptor. It basically takes this chlorine and both of their electrons and turns it into AlCl4-, and that leaves behind our nucleophile, which is, I'm just going to draw this another way around.
Nucleophile or electrophile?
Sorry, did I say nucleophile again?
You did.
Sorry, dude. Electrophile, which leaves us with our electrophile, because I think it's got a positive charge, and then the word nucleophile pops in my head. Too much coffee, I think. Anyway, so we've got our COCH3 plus. Because that chlorine's left, it's taken 2 electrons with it, we have made an electrophile. I'm going to get that tattooed on the back of my hand, mate. So that's our electrophile. But the thing is, from there, the mechanism is exactly the same. So we've got our C double bond O CH3 here. The bond from the hydrogen breaks just like it did before. And then, of course, we end up with our acylated version of our benzene ring here, which is like it's basically like a ketone now, okay, that we've got here. So this is a precursor for lots of other things as well. So acylation, you need to know how we generate this electrophile here. I'm going to keep saying it because so our electrophile there, of course, what gets regenerated later on from this is your AlCl3. So when we've got this, you know, think of the AlCl3 just babysitting that chlorine for a little while. Of course, this hydrogen that comes off is now a H+. So the H+ that we've booted out, that we've substituted, reacts with the AlCl4-, and that gives us our AlCl3 back and HCl. Okay, so that's our byproduct is HCl, and we are reforming this AlCl3, hence why it's a catalyst, because it doesn't get used up and it's not chemically changed overall in the reaction. Okay, so that's your acylation. And like
what's the molecule called? If you've still got the old name nitrobenzene down there, so can you just pull it out and just name our new benzene ring for us?
I can. This is, what is this? This
acyl benzene, is it that simple?
Yeah, it's, I can't remember now. It's gone out of my head.
Any guesses? Andy, can you help us out? Anyone watching? What's that called? I've got no idea.
Yeah, what is that called? That is a very good point. What is that called? It's definitely phenyl ethanone. Phenyl ethanone. This is the ethanone bit.
Oh, you got the
okay,
two carbons.
2 carbons. Yeah. For ethanone, it's a ketone group. C double bond O in the middle of a carbon chain. And because we're treating the benzene as a side chain here, that's where the phenyl comes from. So it's phenyl ethanone. Testing me there, Rich.
Ali said, what was the reagent for this reaction called? Is there one? The reagent, that's not the catalyst. The catalyst is aluminium chloride.
Our reagent here, it is, it's ethyl chloride. Yeah, ethyl chloride.
Yeah, yeah, I see it. Yeah.
Yeah. Okay, so that's our acyl chloride that we've got there, our acid chloride. And AlCl3 is just aluminium chloride. That's our catalyst in this reaction as well. Okay.
Awesome.
So
So
awesome.
what we'll come back, we'll do maybe tag it on. If it's Edexcel only, maybe we'll do it at the end of the next session. Maybe Rich, the last we can always.
I think so. I think if there's if you guys have got any particular requests for next week, I'm going to look at SN1, SN2. If it's something you're interested in, just go ahead and email me, chemistry@tailoredtutors.co.uk. And you know what, if we get enough votes for it, then I'll make sure I put that in. Don't want to disappoint anybody, but we want to try and help as many people as possible. And me spending 20 minutes on something that 9 out of 10 people don't do, that's not going to be very helpful for most people, is it? So yeah, we'll see. But like I said, email me, chemistry@tailoredtutors.co.uk. Happy to receive requests, because next week it's our last one, isn't it, mate? It's our last.
So next week we're gonna have a few more people paying attention to us next week.
Yeah, we are.
You're in the room, so you guys who are here, you can be helping us answer all the questions we're going to get from lots of new students who are going to be joining us next for the last week of September. So bank up all those questions. Any weird, is it on the course? Ward is asking the SM1, SM2. Is it year 1 or year 2, Rich? I know that there's a few little.
It will be in year 1. So it's based on the nucleophilic substitution reaction. So there's 2 different theories, or 2 different ways that reaction can go, SN1 and SN2, in terms of the mechanism. Like I said, it's just Edexcel. It is absolutely not AQA or OCR or any other exam board that we do. I think it's probably on Cambridge International as well, but we don't do that. So
that's basically it. Stay tuned for next week, and there'll be all those competitions to win. So keep your eyes peeled for those. There'll be probably a biology, chemistry, and maths course. For sure, there's probably going to be more or less at least a course or a subscription per day that will be given away. So see you tomorrow for a bit of maths. If any of you are A-level maths students, again, feel free to share this away with anyone doing your courses. If you've got classmates who are doing it, they can join us next week. They can try it out. Obviously, for free next week as well. So that's going to be kind of handy. We'll let you know all the details next week.
It's going to be a real busy session next week, guys, and we've got a few more people coming. So you guys that have been with us over the last few weeks, like I say, take advantage. If you want me to do something in particular, because I'd like that, actually, because if we've got like 300 people watching next week and everyone's asking questions, then I won't know which way to go. So give me some stuff to go with for next week, maybe some year 1 stuff. This has been very year 2 heavy. So send me an email, let me know what it is you'd like me to go over. I would be very grateful, actually. So that'd be awesome.
Great. Okay. Well, thanks, guys. I'll leave Rich to end the YouTube live for us.
Yeah, I'll do that now, and I'll see you all next week, guys.
Yeah, next week or tomorrow.
On tomorrow, yeah, absolutely.